Seated and quiet, please. The first speaker is Professor Philippos Sophos. He's an associate professor in the university on the Department of Physics at the University of Thessaly, Greece. His academic and research work focuses on condensed matter physics and computational physics, with particular emphasis on the use of numerical simulation to study the behavior of matter and at the nanoscale. He received his PhD in 2009 with research focusing on nanoscale fluid flows using numerical simulation and modular dynamic methods. His research interests include the properties and transport of fluids, solid-liquid interaction, novel materials, and the application of artificial intelligence and machine learning techniques to problems in physics. Professor Sophos is also a member of the Condensed Matter Physics Laboratory at the University of Thessaly. Through his research and teaching, he contributes to the development of the computational approaches for understanding complex physical systems and nanoscale phenomena. Mr. Sophos, take the stage.
Thank you for the introduction. Good morning to everybody. In this presentation, we will see how we can add physics inside the artificial intelligence framework, how we can apply our known methods on machine learning and artificial intelligence, and combine physics in it so that we can understand it. It's a major problem nowadays to be more interpretable, more explainable when we use the methods that we use. So physics is a field that has to contribute a lot, I think, in this new era of artificial intelligence. Here we will see, first of all, machine learning and physics, how they are combined. We have 4 steps here, 4 regions of research. How we manage the data. We usually have large data sets to process here, and we need high-quality data in order to train our models. It's a fact that if we train our models with low-quality data, then we won't have good predictions. We have to create models that combine all the branches of science and technology. And these models must be computationally efficient so that we can run them in our laptop. We don't need only HPCs. And finally, what I said before, we focus on the explainability of the result. We have to be able to explain what we see, to be able to explain what we got. Does it have a physical meaning? Does it comply with physical laws, or it's something, just a black box that we don't know where it came from? If we check how machine learning proceeds, we can see that it differs from classical programming. In classical programming, we have the data, we have the program, and we generate the output. Now, with machine learning, we have the output. We need the output along with the input data so that we can create models. So our focus is on the program only. The program is a model that will combine input and output data and give us predictions for future data that will come. The 3 well-known categories of machine learning are supervised learning, for start. This is the most useful, the most practical aspect of machine learning, where we know the data and their labels. We know what they are. We just have an Excel spreadsheet, for example, and we know that this column corresponds to temperature, this corresponds to pressure, etc. So we want to find a relationship that connects the output with the inputs. Depending on how many inputs we give, then we can extract a correlation for the output. That is not the case for unsupervised learning, the second category here. Unsupervised learning takes data where we don't know what they are. For example, we may take data from a distant telescope, and we don't know what they are. What are we going to discover if we process this data? Unsupervised learning is the answer to this. And reinforcement learning is a more dynamic method that can generate new data and improves self-learning. So we don't need much of this. The model will learn by itself just by feeding it with some data. Regression is our first method that we usually use here. It will give us answer to the questions of how much or how many. It's much like the statistical method of the least squares, where we have a linear relationship that connects an input x with the output y, a polynomial relationship, or a combination of inputs, x1, x2, x3, that gives us the variable y. Some examples. If we have, for example, on the first diagram on the left, if we have measured experimentally the momentum versus velocity, then from the slope of the diagram, let's have it here, never mind. From the slope of the diagram here, we can calculate the mass. And that would be very useful for systems that we don't know the mass. For example, when we search for new particles, I don't know, something like this. Or we can extract an equation of state. What's an equation of state? A relation that connects pressure, volume, temperature. And we see a diagram here, pressure over versus volume of a material, of a gas, a fluid, for various temperatures in isotherms. Classification is somehow different. We don't need to know how many or how much, but we need to find which category does the problem belongs to. Or what is the identity of this element. If you see here, we have two classes and one line that separates them. This means that all the measurements that are above the line go to class 1. All the measurements that go down the line are class 2. Examples. Which particle was it? We measured particles and their properties during an experiment, for example, at the LHC at CERN, and we found that photons are the blue ones, the blue dots. Electrons are the orange dots, and they're separated by one line, the region here and here. Or how we can sort the galaxies from their parameters. What is the amount of light, what's the geometrical characteristic of the celestial body we see, and we can see that we can have 3 classes there. And now, the clustering is the unsupervised method. What we create here, we create clusters. We group data. Data that belong to the same group share the same characteristics, similar characteristics. And particles that outside the cluster are very different from the other cluster. This is used to automatically discover new patterns and group this data. Here, in our problem, we will see how we apply AI and machine learning in materials. So if we take some experimental measures for some measures densities and atom mobility, we can find that gases, liquids, and solids create 3 different clusters. So we can differentiate between these 3. Or when we look at the sky and take some data from the sky there, we can see that white dwarfs, ordinary stars, and no giants create clusters of their own. But we see something new there, a small group that nobody expected. This might be a new kind of celestial body. That's how clustering works. We don't know where the data refer to, but we may be helped to describe what is new. So we need a lot of data. That's the main point we start from. Observations, historical data, experiments, all this, computational techniques, all this give us data, and we need them to go further. Before we use them, we have to analyze them. Statistical analysis is the next step. Data needs pre-processing. I'll show you next some slides. And after that, we are ready to apply them to the model and extract the information, find the relationship, etc. What we mean by pre-processing, if you check on the first upper figure here on the left, you can see that we have a cluster of points, the blue ones, and one outlier, the isolated point on the corner, the red one. That means that probably it will create a problem if we take it in our calculations. Why? Because it's very far, and it will go the methodology somewhere that it might be erroneous. So, do we have to reject it, or we have to take it into account for our calculations? That's something that we always are asked to answer. For example, when we are given a table of values, sometimes we may see none here, no record. We didn't get the measure. We had a problem. The electricity came down and we didn't get the measure. So what happens here? Do we consider this value? Do we connect it somehow with the previous value or reject it? And another step for the pre-processing is normalization of data. What means normalization? It means that we restrict them to a range that it doesn't affect the algorithms. For example, we don't want to have values of 0.1, 0.2, and 1 million at the same data set. This means that it's difficult to take them into account for the algorithm. It won't work well. The algorithms that we deal with machine learning, belong in 2 main categories, shallow learning and deep learning. What is shallow learning? It's our first computational kit where we have linear regression, decision trees, support vector machines, and many other algorithms that are very easy to use for our everyday data, for medium-sized databases. But when we have to take into account huge data, image data, experimental data from CERN, etc., then we need to go to deep learning. What is deep learning? It has neural networks, a term that we always hear when we study AI and machine learning. We also have convolutional neural networks, recurrent neural networks, where we take also the parameter of time in the calculations, transformers, and more. Moreover, during the past years, we have managed to get physics inside the neural networks and created the pins, the physics-informed neural networks. I will show you some slides below because I think it's something that physicists must be interested into. a graphical example of the algorithms I showed you. The linear regression is the combination of the inputs that give us an output y. Their variants are Ridge and Lasso. Support vector regression is another method, etc. And one also visual example to see what is deep learning from the simple artificial neural network on the left to the convolutional neural network, where if we see imaging, pattern recognition, etc., then convolutions are the main operation there. U-nets, the pins, as we said before, and all these methods. What's the interest? What do the scientists deal with? Which is the method they prefer? As you can see, deep learning holds the greater amount, about 90%. The simple machine learning, the shallow machine learning algorithms are still used, but for research now they're a bit outdated. We have more data and we need deep learning techniques, like the U-nets, the artificial neural networks, the transformers, which is rising, as you see, as we go towards 2026. What is a convolutional neural network? Let's see it from another side. If we have an image, then we have just raw pixels. What is a pixel? If you see here on the image, we have 784 dots. Every dot is a value. So what a deep learning algorithm can recognize from it? I would say nothing. Why is that? Because we have to give them a hidden parameter, like how many edges exist there. How many arms are created inside the image. These are deeper characteristics we extract from the image with convolutional neural networks that gives us an idea of what is this celestial body, for example. As you can see here in this simple example, it understood that it's by 93% accuracy, it's a spiral celestial body. It's not an elliptical or irregular. And how a simple neural network works? We have one input, X, one bias, and two weights, W0 and W1. If we multiply the weights with X and add W0, then we get an output Y. The real values are the orange dots, and the network S is the blue one. As the neural network works, it adjusts the weights so that we get a guess just above the real values. This means that the loss is almost zero, and our problem is our model is fully trained. What does it mean? It means that we have the values of W1 and W0, and we have an expression that gives us the output. That works both for X values that we already have and for X values that we will have in the future for a problem we don't know yet. And how about physics? I talked a lot about physics, but haven't shown you something. Let's have a cup of coffee that cools down here. It's a fresh coffee at 90 degrees Celsius. The room is about 20 degrees, and we can take 3 measurements of the coffee, of the temperature. You can see them, only the 3 dots. We didn't have time to take more measurements. And we want to see how the temperature decreases. It shows here with the dotted line how it increases, but we have only these 3 measurements. The fact is here, can we reproduce the real phenomenon? Can we add physics? The Newton law of cooling, for example. The temperature will be about 20 to 23 degrees after 10 minutes. Can we see it somehow with a relation? The answer is yes, basically. It's the physics-informed neural networks that have been introduced during the past years, in 2019, for example. They were originally presented for fluid dynamics methods, where we have many differential equations which are difficult to solve. And what is this? It's a kind of solving difficult equations with neural networks. How is that? By using the computational power of neural networks and adding some physics inside them, so that physics drive the problem. In this way, we are sure that we don't violate the laws of physics. So, by having them, we have physically valid predictions. And in the problem I showed you before with a cup of coffee, we have only the 3 points to train the network and an expression, the physics that we know, the Newton's law of cooling. What's this? It's a differential equation with temperatures. So, how it works? It works with the common laws that the neural network has, the data laws that you see here in orange. It came close, but it's not accurate yet. Then we add the physics laws. We add the equation inside it. And even only with 3 points, we get the blue line, which fits to the original, to the expected behavior. And that's the power of pins. Another branch of getting physics inside AI is to get analytical expressions from it. As I showed you before, when we have a bunch of data, experimental data, measurements, etc., and we apply our machine learning algorithm, then we can have a numerical solution where we get the output versus the inputs, and we don't know this relation, but there's a way to discover it and apply an analytical expression that fully connects the input with the output. It may not be linear, like linear regression. It may be of any kind. That's the concept of symbolic regression that we'll show you next. What's this? It's a class of genetic programming methods. This belongs to the general evolutionary computing ideas. What we have here, we have a prediction which may have a physical significance. We have a bunch of data, and we get relations from the data without knowing before what's the relation of the data. We don't know. No one has ever discovered this, and we try with machine learning to give an idea of it. How it works? It works as the population, as the genetic programming suggests. We have an initial population. That's from genetics. We take a random equation and say that this fits to the data. Does it? Let's calculate the error. Do we have mean squared error that is close to them? If it does not, then we change the relation a bit. We make many iterations here. We have thousands of iterations. New child equations are created. Are they accurate enough? Or we have to do the same process again? If it is, then we have a strong iteration, we stop, and we get one relation. We have all the inputs here, x1 to x9, for example. We have all the operations, all the mathematical operators we can use, and then we try to create, by hand, a new symbolic expression. This symbolic expression is given here on the right with a tree. It's a tree-based. It doesn't mean that we have trees. It means that we get the tree here, starting from the upper side, E on x9 minus 2.8, etc. And I will give you this in a small video where we have a problem. We have the coffee data, the orange dots, and we want to create a new relation to say that the way that temperature decreases is given by one relation that I know from symbolic regression. How is this made? Let's start. We start from a random formula. This is a random formula, T. 20 plus 70 times T. How wrong is this? It has a big loss. Let's try and change the parameters of the tree until the blue line fits with the orange dots. That's a question here. We try a lot of things. We reject the tries that are not very correct. And we see that after many iterations, we approach the orange dots. And finally, we get a relation from the data. So we didn't know before what's the relation, how the coffee cools down, but we found it. Are we sure that it is the correct one? We're not sure. We have to check it. That's where physics comes here, because if we know the problem and we know the parameters that affect it, we may find that it depends on time, on the exponential of time, for example. That's what we found in an old physics book. Something like this. Did we create it from scratch? The fact is that we found it without informing the model that it must go this way. And that's the new concept that symbolic regression has to provide us. This was the introduction. Now I will give you some applications of all this that I showed before. The presentation is about the 4 states of matter: solids, liquids, gases, and plasma. How did we apply the methods that we saw before to each one of these 4 states? And how our research gave us results that we may take into account after that. We know that in solids, the particles are locked in their place. They are only vibrating, depending on the temperature mainly. In liquids, we have a more chaotic behavior. They are free to slide past each other. In gases, we have an even more chaotic behavior. Because they are far apart, they're flying fast, they're bouncing off everything. And in plasma, we have extreme conditions. What is the extreme condition? We have very high temperature. So, the very high temperature, in this temperature, atoms break up. We have ions, we have electrons flowing with the other particles, and we have a very difficult problem to deal with. How we get from atoms to properties? Our main job in material science is, apart from experiments, where we have the ability to do so because they are very expensive, we also perform computational techniques. We simulate the problem. A very good method at the atomic scale is molecular dynamics. This approaches matter as particles, as distinct particles, which interact with each other. We just apply the Newton law, the second law of Newton, and count the collisions between them. But this kind of simulation usually needs hours or days if the system is bigger to get a result. So it's not very easy always to do so. It will be very accurate, very physics related, but it may need much effort from us. If we have a database of simulations and we keep the properties of them, then we can train a machine learning model, and the properties that otherwise needed hours to calculate, now in some seconds we have an answer. We apply a machine learning method and we check if the machine learning agrees with MD. So that's a surrogate model. We use the simulations, which are high quality data, to train our model, and then we apply one of our algorithms, whichever we want, and fits there, to get predictions for new states. For example, if we have very high conditions, very high temperature, pressure, we are the space. We can't go at the space and perform an experiment. We make a simulation. Or we apply machine learning and see what happens in these extreme conditions, what to expect. This may not be 100% accurate, but most of the times, if the training data are of good quality, then we can have a very good approach. We can also simulate at multiple scales. What's this? This means that from quantum mechanics, where we are in the scale of angstroms and femtoseconds, which are very small scales, not to the system level, we can get information, and this information passes to the next scale. For example, to nanometers and picoseconds. During these steps, the 4 steps, we approached the system. What's the system? What we see now. It's very easy, and we want it to have system values with quantum accuracy. For example, if we count the properties of plasma inside a reactor, a fusion reactor, at the smallest level, at the quantum level, then we can extract these properties and have an expression, for example, for power at the system level, which is very, very accurate. I will show you now how we approached a problem of diffusion. What is the diffusion? Diffusion of a particle, I will show you a video here. We have the blue particle. It's inside an environment, a dense fluid and a sparse fluid. And we will see how this particle moves inside the general fluid. Consider that you have ink and throw it inside a glass of water. Then the glass of water with the blue ink inside, only a dot of ink, becomes blue. What's this? Is the diffusion. It's how it diffuses inside the water. As you see here, if we have a dense fluid, then diffusion is somehow small. In sparse fluid, it's high. And if we count it, the mean square displacement, we can see that the sparse fluid is very high, the diffusion here is high, and on the left, it's very, it's smaller. We want to approach this behavior with our models. But is it so simple? We have high density fluid, small diffusion, low density fluid, high diffusion. Or the problem is more complex. If you see here, we have increased temperature, very hot fluid on the right. If the fluid is very hot, then we would expect that diffusion would be very high. But it's not. Why? Because the fluid particles are vibrating very fast. They got an amount of energy, a high amount of energy, and this led to smaller diffusion. So, having this in mind from our physics side, we apply symbolic regression and try to understand which of these relations are closer to the physics we expect. As you see here, we don't have an expression from theory for diffusion. That's why we dealt with this problem. We have some empirical relations like the one on the right, which is not very accurate, and it's empirical. And we got 3 relations and want to check which one is closer to physics. The second one, we found after a lot of study that it's closer because it has the term T over rho, the density, and it also has a minus term with T, which captures the phenomenon of when we have high temperature, the diffusion decreases. This is very accurate, and it was found to be more accurate than the empirical relation I showed you before, and it was found with symbolic regression. Symbolic regression also was able to distinct with clustering methods between the states of matter. You can see here that we have a temperature versus density diagram. Then we can see in which part of the diagram, of this phase diagram, the fluid is vapor, liquid, or solid state, or supercritical with the green ones. The clustering method. The same one was also applied on two other properties which are very important and very, very difficult to measure and calculate, viscosity and thermal conductivity. We found that our model with symbolic regression approaches the main theoretical relation coming from the Innsbruck theory of dilute gases. That's a theory from the 60s, 70s, where we also found that our model really finds the same relationship for the problem. Let's go now to the fourth state of the matter, the plasma inside a reactor, the stellarator. That comes from a cooperation we have with Max Planck Institute in Germany, and where a stellarator, W7X, is the researchers there investigate how we can get the most out of fusion to use it for our energy demands in a real stellarator with real experiments. What happens inside the stellarator? The plasma inside the stellarator is a twisted torus. We have magnetic field lines inside it and charged particles that stream along these lines. The plasma is not allowed to touch the wall because the temperatures are very high. No material could deal with them. And it is confined there. And the researchers gave us all the experimental data from the experiments that were held during the past years, and we tried to extract some relations from them. Here's another view of the stellarator. We have ports where we measure some quantities like the power, like the temperature, etc. The experimental data are shown on the bottom here, and we found that the experimental data with our methods, with symbolic regression, give us an expression for the power which is not known, was not known, and it was very helpful for researchers there at the stellarator to calculate the reactor pressure at various conditions. And this is also something that can drive the experiments. They would say, if you want to start the experiment, use this relation and start from here. If you find that this relation are connect with the reality, then we are at a good stage. We can use this method to go further and faster. At the exit of the stellarator now, we have problems with temperature. What's this? We mean that we have to cool down the gas flowing from the stellarator, and we have a hot wall and a cold wall. If we apply our usual simulation methods here, we see what happens when an atom hits a wall. The incident here, you can see it. We can see how the particle is reflected from the wall. It exchanges energy. For example, when it hits the hot wall, it gets hotter. When it hits the cold wall, it cools down. That's something that we can find at the exit of some reactors like this. This is not from real data, it's from computational data from our simulations. And what we got from this, we got, let's say that we got some kernels. These are supposed to be kernels. We can see that the simulation and the regression and the symbolic regression output is similar. That's what we want. And we can also get a relation for the flow. I won't stay more to this. And as I said, we deal with the four states of matter. Let's go now to human flows, respiratory flows, for example, where we have inside the lungs. We also dealt with, we also applied our models because the models are the same. whichever problem it is, then we can apply in our models if we know that they are correct. Here we have real hospital data from the University Hospital of University of Thessaly from COVID-19 patients. And we apply our symbolic classification now, not regression method, to examine the mortality of the patients. As we see here, we have about 50 parameters and want to find which of them is important for the problem. We found that about 8 of them are very important, and they decide, they don't define, the mortality of the patient. If we have these 8 values, then the doctor can, and the nurses can do more focused investigation on these values to see how the health of a patient will proceed. We have an analytical relation for this. If a doctor can have it in his Excel or his phone and get the result to see if the patient has a very serious problem or not. We can also study respiratory flows inside the lungs to detect pneumonia. How we do this, apart from our simulations we perform with the air flowing inside the lungs, we can also extract useful features from the images, from these X-ray images, and apply the same model of symbolic classification to see if we have pneumonia or not. Here the problem is that we cannot have always real data, so a model, creating a model of a patient, a tube, and the gas flowing inside it to see where we have a problem. How much time can the air flow? With what velocity? What's the pressure? What's the most critical value? You see here on the left a red one. A red one means danger. We cannot leave it for many time. We cannot have this supply of oxygen for so long. And I go on with turbulent flows. As I said before, this is the region of research where PINS started. And why they started from here, the highly diffusive nature of turbulent flows, as you can see, causes rapid mixing, increases rate of mass, momentum, and energy transfer. This is a very chaotic and difficult problem. It has very difficult partial differential equations to solve. So what we do, can we solve them? We numerically solve them usually, not analytically. We cannot do it. These are the Navier-Stokes equation and the conservation of mass below. If we take these equations now and add it inside the loss function of a neural network, then we might have a very good model. Do we have? We indeed have a very good model. And if we also apply symbolic regression, then we can have. I show you just this example to have a general idea. We can have regions. Here is the velocity inside the channel. We can have regions that are very close to reality, both with PINS and symbolic regression. And if we expand the problem in fluid dynamics with sensors, this may be sensors in the air, sensors inside a channel flow, or even sensors inside a forest where we want to check if fire exists. Then from these sensors and our deep learning techniques, we can get a full-scale value. See from the array on the in the middle here, we have 16 values. These values are discrete with color, but if we have a trained model like the one on the bottom here, on the right bottom, with convolutional neural networks, then we can recreate this model and give a detailed field like this one. Here we have an image of temperature, density, I don't know, whatever. a general property of interest. We can have it in full scale, such as a pressure field in airplane wings, velocity in turbulent flows, as you see here, temperature field inside a room. This, for example, comes from a project that finds temperature inside a cabin of a ship cabin, where we have an air conditioning device on the ceiling, and they want to count the temperature field in various levels inside the room. And of course, all these methods can also be applied in engineering, for example. Civil engineers have used these methods to see if the concrete they use is strong or not, or what they need to do to make it stronger. An architectural, another one application that finds which feature is important to have an energy-saving building. For example, the air tightness, the size of the windows, etc. I passed it very fast. We are approaching. So, we have seen that all these methods, even when applied to different regions of science and technology, we may have a general idea of how to use them in our problem. Imagine how to use them in your data. I don't know what they may be. But have in mind, don't forget the physics, I would say. Everyone does machine learning and AI and tries to do AI. Even a simple user on an LLM now considers himself or herself that he or she does AI. But I say that the application must be delimited so as not to violate the laws of nature. This is how we can build more efficient systems and more closer to reality, because we don't want fake results, we want real results. And that's from our condensed matter physics laboratory in Lamia, in the Department of Physics, where we applied similar methods. This can be applied not only to condensed matter physics, as we saw, but in economic, social, medical, and other natural systems with all these methods. And that's all I had to say. If you want to find more or publications related to these slides I showed you, you can visit our lab. And thank you now. I'm waiting for your questions. Ωραία. Ευχαριστώ πολύ.
What software product do you use to get these equations and diagrams?
We mainly use anything with Python. You can start with Python in any kind of software, and you need specialized software when you do only simulations. If you want to do machine learning, then I think with Python, and especially a graphical environment like the Jupyter notebooks, you can find many things on the internet to start with.
All right, thank you.
Okay.
Έχει κανένα USB 3? Όχι.
Είναι εδώ, βάλτε. Βάλτε το.
Θα αργήσει πολύ. Είναι 4 παρουσιάσεις. Πού τα βάζω στην desktop? Εντάξει, εκεί.
Και αυτό εδώ είναι για τον boiler. Είναι για το... Έτσι ώστε πάει στην επόμενη, έτσι στην
Εντάξει,
προηγούμενη.
αλλά δεν θα φύγω από εδώ γιατί είδα δεν ακούγεται.
Και με το βελάκι.
Το ξαναβάλουμε μετά.
Όχι, και να μην χαθεί.
Ναι. Εγώ έχω 4. Όσο καλά και να είναι.
Ελάτε λίγο εδώ. Μην κάθεστε μπροστά στην
Δεν κάθομαι.
για να δείτε και να κάθεστε σε κάτι.
Όχι, επειδή έχει τα βίντεο να πω. Τα πήρα έτσι, εντάξει.
Λοιπόν, να ξεκινήσουμε με τον δεύτερο μιλητή. Παρακαλώ, πολύ ησυχία. Συνεχίζουμε με τον κύριο we continue with Dimitrios Jovaras. Dr. Dimitrios Jovaras is a distinguished Greek researcher in the fields of artificial intelligence, computer vision, machine learning, and virtual and augmented reality. He is a senior researcher at the Center for Research and Technology Hellas and has held senior leadership position within the organization. He received his diploma in electrical engineering in 1992 and his PhD in electrical and computer engineering in 1997 from Aristotle University of Thessaloniki. His doctoral research focused on two-dimensional and three-dimensional image compression. Dr. Jovaras has extensive research experience in computer vision, visual analytics, multidimensional data analysis, machine learning, artificial intelligence, biometrics, and virtual and augmented reality. His work has also contributed to practical application in areas such as medicine, energy, transportation, industry, and cultural heritage. From 2010 to 2018, he served as a visiting professor at Imperial College of London, and he has also served as a visiting professor at the University of Nicosia. He has participated in numerous European and national research projects and has collaborated with major international companies, including Samsung. Dr. Jovaras has made a significant contribution to research, innovation, and mentorship. He has been involved in the creation of spin-off companies and has worked as a native promoting the development and practical application of emerging technology. Overall, Dr. Dimitrios Jovaras is recognized as an important figure in Greek research and technological innovation, particularly in the rapidly developing fields as artificial intelligence and digital technologies. Mr. Jovara, stage is yours.
Good morning, everyone. Thank you very much for the introduction. A little bit lengthy, but I'm more than 30 years in the R&D, so I have a lot of things to talk about. What you did not refer to is that the last 15 years I'm mainly on managerial positions at CERT and the Information Technologies Institute. And what I will be presenting to you today is mainly the work of my group. And I would first like to, thank you very much, to start with a short introduction of CERT. CERT is one of the 11 research centers in Greece. And it's actually located less than 500 meters, one kilometer from here. So it was very easy for me to come first, and second, it would be also a good opportunity for you to visit in the future. So CERT, as a research center, focuses not as a university, as academic institution on teaching, but on research. And mainly for CERT, basic research is one of the issues for some of the groups, but applied research is an issue for all the groups. We are now more than 1,700 people with a large number of publications and a very positive outcome in our evaluations. And the annual turnover of CERT is around 70 million, which puts us in the first position in Greece, which is rather not typical in Greece that an organization in North Greece and Thessaloniki is in the first position. And what is interesting for today is that we are in the first 11 institutions in Europe in competitive research funding in Horizon Europe, and we are in top 5 in AI-related research funding. So that's why I'm going to present to you a number of research results from various projects that we are currently implementing. CERT has 5 institutes. I will not go into details. It's mainly information communication technologies, where I come from, energy and chemical processes, applied biosciences, agriculture and bioeconomy, and transport. So these are the areas that we are targeting in our institutes. We have subsidiaries in many areas in Greece, but the main premises are here in Thessaloniki, and with a lot of research and innovation facilities funded by the government, and also a lot of projects. What is important, and I would like to mention, is that since 2013, CERT has started supporting a lot of spin-off companies. Now we have 23 spin-off companies, and some of them are very successful. Actually, 2 of them, Optimums and Pragma IoT, and some others have a lot of potential. So we, the last years, we are also dealing with issues like entrepreneurship. So what I will be presenting today, and I have 3 separate presentations, is applications of AI and R&D results of various AI projects that we are running in 3 domains in health, coming from the Visual Analytics Lab of Information Technologies Institute of CERT, robotics coming from the Cognitive Systems and Robotics Lab, and simulation coming from the Virtual and Augmented Reality Lab. So that's all for the introductory slides. So now I start with the first presentation. Let me see. Okay. Everything is okay. So I will start with the focus that we have on research in health-related issues and the revolution that AI is currently bringing to health-related research. You can see that concerning the use of AI in healthcare, there is a growing demand the last years. COVID was, in one more case, actually the accelerator for applying this AI technologies on that. And the top trends are on diagnostics, they are on agents to support personalized healthcare, on predictive analytics for disease prevention, for also on robotics and surgery, which is now a common practice, I would say. Also on remote patient monitoring and telemedicine, and especially on pharmaceutics, research on new medicine comes mainly using a lot of Gen AI models. Let me show you an example what AI can bring. Actually, in a case like wet AMD, which is an ophthalmological disease, which can end up with actually partial vision loss or complete vision loss. It can actually detect 2 visits before having actual symptoms the presence of this disease, and it could be, this is in this particular case a revolution, since before any kind of vision loss you are able to tackle to deal with the specific disease. In terms of drug discovery, traditional method, 10 to 15 years, a lot of money invested. With AI solutions in all the stages, it may come to 5 to 7 years with a lot of savings, more than 50%. So, and these numbers are improving daily in terms of how much this is moving forward. For example, most of the drug discovery research currently is done through simulation. So you don't need clinical trials. In some of the cases, you can simulate also the clinical trials. And how can you do this? Is by improving this, what we call patient digital twins. I don't know if you heard the term digital twins. It's now a trend everywhere. It's similar to think about that on the architecture engineering. So you have a digital twin, you can apply, you can simulate. Before you build, you can run any kind of simulation. What actually is happening in healthcare is that we can have a digital twin of a human being. And this digital twin could be a digital twin of me, and not of any man, 56 years old Greek. It could be a digital twin of me, having all my data, all genetics information, my habits, my real-world data collected by various sensors. So this is what we believe is the future, and of course, there are many challenges on applying AI, having to do with algorithmic bias, with privacy, and also ethical issues, and of course, all this have to be tackled in order to have a valid application. So this was an introduction of where healthcare is leading with AI. My presentation is the presentation of an engineer. It's not the presentation, so you will understand. So my focus is on the result, and my focus is to show how we can apply our research on real problems. For example,
China has unveiled the world's first AI-powered hospital, staffed with 14 AI doctors and 4.
Okay. Just an example of what's happening currently in China. 14 robotic doctors, 4 nurses,
and
in
4
an AI
fully
hospital,
autonomous AI nursing
2025.
agents.
Okay, this is coming everywhere, and this is where we would like to contribute our research. Now, I'm moving to more. I showed this video only to see that things that were on sci-fi movies are coming to reality. What I'm going to present now is the work of our visual analytic lab from 2020 up to today on the use of AI on various tools that we have developed. What I would like to mention, what you will see is on actual use on real environments. It's not a result in experiments in the lab. So, for example, we have worked since a European project called My Air Coach to develop an asthma AI virtual assistant. Actually, we have two versions of this assistant. One version is with speech recognition for the physicians, for the doctors, to use a clinical platform for monitoring the progress of the disease of patients. And the other is for patients, an agent to actually help them answer questions and help them monitor their condition. What we have used, and you will see, this is a model that we used on 2020. It was the diet model, and we actually parameterized and fine-tuned this model for asthma applications. And in the same direction for asthma and COPD, very similar diseases, completely different, but similar. There is a big challenge on the use of the inhaler, and we have developed a novel approach for the usage of inhaler, which actually integrates camera and acoustic sensor, and we are able to actually see how the patient is actually using the inhaler and correct on the fly what the patient is doing. You can see some pictures of how this can be applied. And at the end, we know whether this has been used correctly or it has to be repeated. And all this information is stored and also communicated to the physician. For chronic heart failure, we did an experiment with pilots in five countries, in Sweden, Portugal, Italy, Greece, and Turkey, in a project called Coral. It was a big European project where we used the GEMA 3 12B LLM model to be able to train it with data that was provided in 5 different languages from all the participating organizations and all the relevant laws and restrictions that each of these countries have, and be able then to provide the agent. It's actually, we are working on the same agent using different models and parameterizing them and fine-tuning them for the particular use in each case. So this is coming from asthma, then we move to chronic heart failure, and this is how you see this can be applied, and you see that this is live and it's actually used in 5 hospitals in these countries, and it supports a number of languages plus English always. You should know that. The same then we had a request from the association, the Greek Association on Hypertension, for an AI virtual assistant to educate patients with hypertension. And we implemented them using an open source model. So this is where we actually created also the model. And we provided this to patients. And this is provided again in Greece and now in some other countries through this, the Greek Association of Hypertension. And last, I think, last instance, I would say, of virtual assistant. It was the Incrodis Plus project, diabetes AI educational virtual assistant. You can see also an example, and again, we have used, it is one of the first applications that we did. We used again the diet model. Then what I would like to present you is the first, I don't know if you know that Pfizer, the big pharmaceutical company, has now a research center in Thessaloniki with more than 2,000 people. When they started, the first contract they gave was to CERT, and this contract was was actually to develop conversational agents for COVID-19, and we were provided with around 4,000 documents from communication that physicians around the world had with employees from Pfizer, and we were actually asked to create an agent to replace actually this whole procedure, and this was done and tested in US with Pfizer, and actually also integrated in a system receiving also force feedback from the real agents. You can see some examples like on application like Ask the Agent and get a reply from the documents, actual chat with an agent, so we support also dialogue and also asking also questions out of the box for the specific example. Again, with Pfizer and in a big European project, IMI project, we have implemented, I think it was 3 years ago, a graph-based model for literature analysis, and as you can see with this visual representation, you are able to identify links between authors, links between similarities between papers and groups of research areas and contributions on these areas. And all this can then be actually further used to improve the research relevant to specific papers. And you can see, for example, if you take one of the papers, you can see what other papers did the authors publish in the same domain or in other domains or in similar domains, where they stand in terms of global status in this research domain and similar subjects. Another application that we have done was on an embodied AI agent for cancer prevention. This was based on GPT-4. This is a completely different approach. Just from the dialogue with the patient, we are able to make some estimations with text and images and to get some emotional aligned information about the status of the patient, and then adapt the dialogue we have with this patient and the avatar that we are using for this interaction accordingly, in order to have the best feedback to the user. This was also part of a European project. Partially then we moved in the same project on the analysis of MRI and CT data we got from hospitals in Greece, in Spain and Italy on prostate and breast cancer. And we have worked a lot on improving results in this direction with that are presented in one of the European projects, the OnCoDIR project. Another area where we have applied AI tools for, in particular, NNUNet, which is actually nothing than one of the approaches of convolutional neural networks. The idea was to be able to reconstruct the human heart using annotated CT scans. We use this for training, and then in taking a new CT scan from a patient, we are able to reconstruct, and you can see how the results look like. And then we are able also to present it in an AR tool, enable for the physician, in order for the physician to actually have a visual representation of stenosis and other types of cases that the patient is suffering from. One of our very recent works, and now I'm moving more to 2025, 2026. This is one of our recent work with Samsung. We have a long-standing collaboration with Samsung Mobile since 2018. And it has to do with creating new foundation models for wearable data analysis. Actually, we are getting data from Samsung devices, smartwatches, mobile device of Samsung, any kind of data that we can utilize. And we are currently working on the prediction of LDL. So this is something that where we apply completely new approaches on the fine-tuning on we're using for on-device adaptation, using nonlinear probing, low-rank adaptation, pruning, distillation, and quantization, the relevant quantization. This is work in progress, and from Samsung it's considered rather innovative, actually to be able to predict the progress of, actually, this is an indicator that can also lead them to some kind of disease. Another approach where we're currently working using GPT OSS 120B model is the interactive dashboards using text prompts. This is a completely new paradigm. So if you have a user prompt you have no information, but based only on the user prompts, you are able to create the visual representation of the information that the patient wants to display or the doctor wants to display. So it is a complete patient agnostic and doctor agnostic, so we don't use user profiles, but only information extracted from the user prompts to create the dashboard. And it's work currently done in a European project called Extra Brain. Now, as another example, I will show you a hackathon where we participated in 2024, which was based actually on the leaflets on what we call electronic product information for. So we have leaflets of various drugs, various medicine, okay? And based on these leaflets, there was a challenge saying, how could you present this electronic information in an optimal way for a particular patient. We got the second prize on this hackathon, and the idea was first to analyze the data using various models. We tested 3 models, and to be able to semantically annotate most of the entities that are relevant to the patient, and to highlight them for the usage by the patients. And another approach was also to link it with the person profile and actually have also a graph-based presentation of various drugs that the patient could be used, and create also a chatbot to make this information easier accessible to the user to be able to answer questions. So what we ended up with is some kind of personalized leaflet, okay? Personalized electronic product information, which actually highlights the most relevant information for the particular user and others, areas that are not relevant to the user are actually faded, as you can see. And another example is that you can provide also relevant information for this user through the chatbot. And very interesting, it was also the graph of drug interactions for the particular user. So we know from the profile what drugs they are currently taking, and we present how these drugs could interact with other drugs that are in the leaflet. So you know that this is for you, or this is not for you, this could be dangerous for you. So this was done, everything was done by the group in hackathon. Actually, it was, I don't remember, some days. And we just wanted to present that all this work on the agents and the introduction of models is, can be reusable. Sorry. And what we are currently working on is a completely LLM-driven medical record management and clinical report analysis. So let me say it in more clear words. Actually, we use speech recognition to get to digitalize the information that is provided by the physician for the patient, link it with similar information for the particular patient, and also introduce it to the electronic health record for this particular patient. So this is an application we have developed the last 2 years, which is actually now running every day live in 3 private and 2 public hospitals in Greece. So it is actually revolutionizes the way that work done. No, there's no paper now. Everything is done electronically. So this approach is something where we are working to optimize, and we get very good feedback from the hospitals. Finishing with my presentation on AI research on health-related issues, we have a test bed since 2016 at CERT, as I said, 1 kilometer from here. It is a fully equipped smart home where you have voice-based control, navigational guidance with augmented reality, emergency detection and assistance, activity monitoring, personalization for the users, and security and privacy integrated by design. So this is a test bed that we have, where we have run a lot of tests also in European pilots. We are a member of the Greek AI factory, called Pharos. Sorry for the Greek, for those that I don't know, most of you probably cannot understand. So this is the new trend in Europe to create AI factories in regional AI factories in various countries and groups of countries. So Greece was one of the first 7 that was assigned an AI factory, and this is called Pharos. And what I wanted to show and how I want to end this presentation on health is what we are currently building. Based on all this expertise that I presented, we are building what we call Gramma 12B, which is fine-tuned LLM model for Greek medical tasks. We have so I don't know if you, in Greece there is a large language model for Greek language called Meltemi, and we are building a Greek model for medical related information, and we call it Gramma. And we have much better results than the others, the CRICRI and the MELTEMI that are published. And we use information from Calipos medical book database and a number of other databases that you can see are listed in this domain. And we are continuously updating this model, and this is our main contribution on Pharos from CERT. So, finalizing my presentation, and before I start with robotics and simulation, so I would like to say that we are afraid that AI will replace doctors. What seems to be, no one knows what will happen. We see that in China they are replacing doctors. But for sure, we can say that will not 100% AI replace doctors, but a doctor who does not know how to use AI will be replaced by someone who does. So this could be as a thing to consider for the new physicians that are entering now the medical domain. That's all from me. More details, you can, of course, contact me and my colleague Kostas Votis. I have actually presented the work of the group of Kostas Votis on the Visual Analytics Lab. And since the title of because I didn't know what to present, the title of my presentation was Applications of AI. The next topic is on robotics, where I would like to show where we are. It's a smaller presentation. Let me see. Okay, I have some time. So, on robotics, again, our group is focusing on challenging scenarios and use cases, so enabling robots to perform complex tasks in demanding, unpredictable, and harsh environments. And we work a lot, as I said, the group works a lot on computer vision and on navigation. So research areas for us, robot vision, SLAM, which is actually reconstruction of the environment, utilizing various sensing information, mainly cameras, but also LiDARs and other things for the navigation. Then modeling of the environment, then human activity and object recognition, then introduction of AI and machine learning, and augmented reality introduction in robotic applications. What I will show you today is some applications on logistics and retail, on the construction sector. I'm not sure you have seen something like what I will show you today. On agriculture, you have seen something on that, like that. And on then rough terrain and dual-use robots. When we say dual-use, is for civilian use, but also for defense. So this is one of our topics where we are targeting the last years. So I start with, and as I said at the beginning, I have some videos here to show. So this is an example. This is a video from a project called Moneybot. It has to do with luggage handling in airports, and it has to do also with manipulation of products in the shelves of supermarkets. Okay, so partners are Fraport for Greece, and the Masoutis supermarket in Greece. And you can see an example. First of all, here you can just see the detection of luggage and actually the manipulation of some objects in cells. What we are working on is on adaptive robot perception, so environmental understanding, object recognition, 6 degrees of freedom pose estimation, sub-parts, for example, you need the handle for the luggage. We are responsible in this project to find this. And the manipulation affordances, this is very important information for the bimanual robot to be able to manipulate. Work on the bimanual robot comes from Aristotle University of Thessaloniki, the group of Professor Dulgeri, and many other partners on that. You want to take a picture on this? No, yes. Okay. It is the Moneybot project. You can find information everywhere. So you can see, okay, well, what I was showing before was an easy scenario. There was a luggage coming in the belt, and there was someone manipulating it. So here is, you see this is 2 times faster than it actually runs. And it is a case where we are applying all the steps of detecting, finding, deciding how to approach, finding the affordances that this particular luggage has, and then the manipulation part from the bimanual robot, which is by itself a very difficult task. We have to decide what the left arm will do and what the right arm will do. I said from the beginning, these are difficult tasks. These are some of the few tasks that have not been yet industrialized. So, and this is where we are now. It's a project that's currently running. And what I would like to show next is Robet Armé, which is a human-robot collaborative construction system for shotcrete digitization and automation through advanced perception, cognition, mobility, and additive manufacturing skills. It involves technologies on BIM, which is actually building the building information model generation, 3D reconstruction on the fly, additive manufacturing in some parts that need corrections, the shortcutting application that you will see, SLAM and navigation. SLAM is, again, finding the actual environment in navigation, orchestration and task planning, and, of course, the part of augmented reality for presenting to the operators, and the part of the part of the human-machine interface. These are some pictures from one of the cases that we had in Alps in France, and maybe it's better that you see this. Maybe I'll stop this one. So there are 2 steps. Oh, just a moment. There are 2 steps. We have 2 versions of the robot, the IRR robot, which is the robot that is doing the inspection and reconnaissance, which visits the site, finds the area, analyzes the area, and measures the actual work to be done, and creates also the tasks and orchestrates how this will be approached. And the SFR is the robot for shotcrete and finishing. So I will stop this one. You see here, for example, this is the first robot for inspection. Robotnik is providing the platform, is a Spanish company. And you see that with various sensors, we are able to reconstruct the actual environment and to decide where and how it will be approached by the other robot to actually do the shotcreting. So you see this, we are in the very infant stages now. But imagine in the future that the whole tunnel can be actually created by robots with no human interaction. So let me now show you what is the second robot doing with shotcreting. You see, we are preparing the shotcrete mixture. And this is what the robot is finally doing in this specific use case that you see in one of the pilot sites in France. So this is a really difficult and harsh environment, and it's robot arm currently finished 2 months ago, and we have what you see is from the actual pilots. Bacchus was another project which is also can relate to American farm school, since it has to do with grapes and harvesting of grapes in agricultural areas. That is one of the most challenging cases we had. You can see some examples. You can see if the day you are doing the actual measurements, there is some air, what happens with the movement of the leaves and how this can actually influence the creation, for example, of the environment. So what we were doing is, first of all, to do the reconstruction of the environments and semantic mapping, then to provide an algorithm for localization of targets, and the understanding of the dynamic environment. What was important is to find the grape, to understand whether this grape is in the condition to be harvested, and then to do this task planning. As you see, for example, this is a reconstruction that we have a model of the grapes in an agricultural installation, and this is the case we have. Just a moment. This is the final demo we had. It was in Gerovasiliou winery in Epanomi in Thessaloniki. It works. Okay, you see what the sensors are actually seeing. It's again a bimanual approach. One actually, we find the actual grape, and then it cuts the stem, and then the other arm is actually putting it into the rover that we have for collecting the grapes. So these are very difficult use cases, and of course, there is a lot of work to be done in this direction. So now I'm going to present for 4 or 5 slides the work of one of our spin-offs. It's Aussie spin-off, comes from our group, which is actually developing this UGV, unmanned ground vehicle that you see. This is a completely autonomous vehicle for navigation and mapping. It performs AI-driven traversability analysis. This is the most difficult task, is to understand the terrain. If you go with a typical approach, you have you will fail for sure. And then we have inspection, also teleoperation that was requested by the partners. GNSS denied navigation with various sensors. You can see some examples here from military exercises of the Greek army, where we were mainly involved in logistics operations. You see an easy example on the left and a much more difficult example on the right when it was raining, and you have to detect the status of the environment. I cannot give more details, but what I can say is that we are continuously going to military exercises of the Greek army, and we hope to have something that could be also finalized as a product for logistics, not only for defense, but also for dual use. And that's I think, the last case. Again, with Fraport, we were asked to develop a robot. This is 100% developed by Aussie. Again, you could say it's nothing new, but it is new. Everything is new. Navigation, object recognition, collision detection. In such an environment, you see this environment has very difficult illumination constraints. Very difficult cases because there are visitors going everywhere, want to play with the robot, and So it is a case that I don't know if some of you came by plane. It is currently operating in the Thessaloniki, Macedonia airport of Thessaloniki, and we are working with Fraport to be able to commercialize it further in other airports. What is interesting is that what it actually performs is a follow me task. So you say, you put your ticket, and it takes you to gate 15, I don't know, whatever, which is just follow me. This is the typical task. What else it does is that whenever it goes around, it can also perform tasks like Wi-Fi signal strength detection. Then temperature, humidity, actually detects people laying on the floor, malfunctioning lights, unattended luggage, malfunctioning monitors that have to be actually replaced. So this is a lot of information that is provided for the technical maintenance of the airport. That's all. This is the group of the Lab of Cognitive Systems and Robotics, led by my colleague Dimitris Giakoumis. I think we have some time. I have another presentation. I can do it in 5 minutes, just not to take time from my friend Leodios. And this is, again, something I consider interesting. It comes again from the defense research that we are doing the last 3 years. It's a multi-agent reinforcement learning approach we have for simulation with a use case on maritime. Just to be fast, what is the case? You have a red team with 3 vessels, a blue team with 3 vessels. You have a target. If it shows Greek islands, I'm not sure, but it could show the Greek islands. And blue and red is not, it is typical in security research, but blue and red could be also realistic. just a comment. And we are actually modeling the environment. G is the environment, N is the number of vessels, S is the state vector we have, the actions are A, O are the observations, P is the state probability, R is the rewards, and gamma is the discount factor for the future rewards. What is interesting is that this model is, again, use case agnostic, which means we just get data from Google Earth. So this is not for a specific region. It can be applied anywhere. We need also data from concerning the terrain. We need data concerning the bathymetry that we can get from the relevant organization in each country, and real weather data. So this is the approach we use. This is a reinforcement learning simulation model. So the approach is that we don't use data for training. We are creating this data for the simulation. And we are creating various scenarios. We are running these scenarios. And as you will see, we need a number of parameters. I will go fast because I want you just to show you this, how reinforcement learning, adversarial reinforcement learning works. We have, first of all, I cannot see very well, we have the observations. We have the proximal policy optimization, so there is a policy per partner for the blue team and for the red team. The action that is taken, and then we have the actual simulation, and then we have the rewards and update of the PPO policy based on the rewards. And what I think is interesting is to see these examples in 2D. So there are 3 blue vessels and 3 red vessels. What you see now is the result, this is something I should mention, of this repetitive procedure run around 20,000 times to converge. So in order to converge, it's run around 20,000 times, and it has to have, in order to get difficult results, you can do also some heuristics. For example, at some steps, we stop the red team and we let the blue team operate. In some other steps, we stop the blue team and let the red team in order to get more examples and to be trained in the different scenarios. What you see here now can be applied to any other maritime case. Okay, that is the interesting part. We are actually training the agent through this simulation. And you can see also the same in 3D, in Unity, when we are loading the model. So this is an example. Yes, there is actually, yes, two of the blue vessels and 3 of the red vessels are eliminated on the left, and on the right, one of the blue vessels eliminated is a different scenario. What you see with red, deep red, and deep blue is the area of the visibility area, but you also see in the radar capture capabilities. And you see now you can have a complete scenario for visualization. This is run from a 15 million euros project called Battleverse with all the European partners inside, big partners, Naval Group and similar partners. We are working on such simulation scenarios, and this is one of the first results from the first year of the project. My colleague Nikos Dimitriou is actually working on that. We would be happy to receive any questions. Sorry if it has taken a little bit more. I wanted to show different things, but mainly really applicable things in realistic and difficult cases. Thank you very much. In which case you mean? In which, because you mean on the health domain, on the robotics? On the robotics, for example.
In the healthcare, you show some videos.
Yes.
Small video. Are they far ahead from us, or what do you think in general?
I think, as a general comment, I think they are far ahead on everything. On everything, not only on health domain. I do believe, on the other hand, that in the health domain we have data that we should not let them get access to, and this data can be actually provide a lot of.
You presented quite a large spectrum of AI applications.
Yes.
It's very nice, but are we the fast followers in all those, or are we leading any of those presentations you cover?
For example, I would say that for the shortcut application, I think we are actually not actually leading, but we are the first, some of the first to tackle it. For the Fraport application, I think there are other workings, but as I said, having a robot moving around doesn't mean that it works on difficult scenarios. So I'm not ready to tell you exactly where we stand. I think that wherever European industry is strong, we are also tackling difficult problems. And where Chinese research is, I'm not sure I know.
The last question.
Yeah.
Are we collaborating with Chinese researchers?
No, we are not allowed.
Okay.
We are not allowed to collaborate.
Thank you very much. Thank you.
You're welcome.
Thank you very much for your presentation. I would like to ask you if there is any AI application in predicting earthquakes.
I'm not aware of anything on that. We are not working in this domain at CERT.
If
Sorry.
you know if there is any...
I haven't heard of something, no. Maybe Leodios have heard of something, I don't know. I haven't heard. Yeah, welcome.
How about the students? Yes, please take the mic.
I really like your presentation, but I have a question. You said that robots will not replace doctors, but in the video you showed us, there were only robots in the
In
lab.
China.
Yes, in
Yes.
China.
And they say they are actually, if you ask me, it's a very difficult question to answer, because first of all, we should ask ourselves if we want to be operated, for example, by a robot that is taking decisions autonomously, or we want to be operated by a robot that is checked or partially controlled by a physician. For example, I would prefer the second case. On the other hand, we need to adapt to new scenarios. What I showed is a video coming from Tsinghua University for I could say pilot case that they are building with robots for help. So I do believe that we, at the beginning, we are using robots currently. Da Vinci robot is used for most of surgical operations, for example. But it's controlled by a human. It's not autonomous. So if the degree of autonomous operation depends on the acceptance from patients, and this could take time.
Okay, thank you.
You're welcome. Yes, please.
You talked about the possible applications of robots in food technology, for example, in the winery that you showed. But how can we ensure that health safety protocols will be as strict as with humans working?
It's easier to put restrictions to the robot than to put restrictions to a human.
But aren't robots using, how to say it, substances, for example, as in lubricants for motors, that are certainly not safe for humans to consume? How can we ensure that there is no contamination of the food?
I think if it goes to the market, I think this will be taken into account in the design of the grippers and things like that. So I don't think there is a problem. Since we trust humans, for sure we should trust robots on doing easy jobs. That's my approach.
Okay, thank you.
I just wanted to follow up, like you said, we should trust robots for easy jobs, and I just wanted to say, like in hospitals, like if we have AI doctors and stuff, that's not very easy. But let's say we have a robot doing a surgery. So like how do we address the problem of accountability? Like what if a robot gives you a wrong dosage of some like pharmaceutical and you die because of that? Because that is like a case study. Or there have been accounts where the robot has malfunctioned or has done something wrong in a more serious situation. And like how do we give it accountability? Because the robot obviously isn't a person who can just say, it's the robot's fault. We have to give accountability somewhere. So how would you address that?
I'm not sure I understood all what you say. I heard about if the robot does a mistake and gives you the dosage, for example, something like that. Yes, I think that robots will be introduced in the everyday medical practice up to a level that can be trusted at the same level as a human can be trusted. For example, autonomous cars are currently operating in LA. Okay, autonomous taxis. Why are they accepted? Because they showed an operation which is similar to the average human and in most of the cases better than the average human. That's why it's accepted to start, and then it's accepted to continue and to improve.
But like humans make mistakes, right? Like when a human makes a mistake, if a taxi driver crashes, we're going to say the taxi driver is at fault.
Yes.
So if a robot driver crashes, then what do we do? Do we say it's the robot's fault, or like what?
If the robot crashes, it's not it is the police problem to say what they will do. It's not my problem.
Oh, okay.
But I think that technology goes up to a level, and when this level is at the same stage or better, I would say, from the current state of the art, from the current situation, as operated by humans or by other machines, I think then it should start being accepted in everyday life. This is it's a very general answer, but I don't have a better answer.
I agree with you on that, yeah, thank you.
You're welcome. Okay. Okay. Thank you very much.
We continue with the last speaker, Professor Leontios Hadjileontiadis. It's a distinguished professor in the Department of Electrical and Computer Engineering at the Aristotle University of Thessaloniki. He also teaches at Khalifa University in Abu Dhabi. He received his diploma in electrical engineering in 1989 and his PhD in electrical and computer engineering in 1997, both from Aristotle University. His research focuses on advanced signal processing, machine learning, biomedical engineering, artificial intelligence, and healthcare technology. Professor Hadjileontiadis has conducted extensive research on biomedical signals, including heart and lung sounds, ECG data, and other physiological signals. His work also includes affective computing, assistive technologies, active and healthy agency, and application of machine learning in medicine. What makes his academic profile particularly unique is his strong connection between science, technology, and music. He holds a diploma in musicology from Aristotle University and a PhD in music composition from the University of York in the United Kingdom. He has explored the relationship between physiological signals, signal processing, and musical composition. Professor Hadjileontiadis has received several international distinctions, including recognition from Microsoft, Reimage Education Awards, and the Dubai Healthcare City Authority, and he is also a senior member of OIEP and has extensive experience coordinating information and international research projects. Overall, Professor Leontios Hadjileontiadis is an incredible researcher and educator whose career combines electrical and computer engineering, artificial intelligence, biomedical research, and music. His work demonstrates how technology and creativity can come together to address important challenges in healthcare and society. There, Leontios, the stage is yours.
διαβάζω από εδώ. Δεν ξέρω, αλλιώς πρέπει να κάνω... Να κάνω κόπη εδώ την παρουσίαση. Να κάνω την παρουσίαση. Ναι, έχω. Να την κάνω την παρουσίαση εδώ. Τίποτα, έβγαλα αυτό. Θα βάλω σε ένα USB να παίξει εδώ. Δεν το χρησιμοποιήσω. Okay. Hello. Good afternoon. The first task I have put to my students is to learn my last name, which is very difficult. But I teach it because my first name has a similarity with the last name. So you do the cross-correlation of my first and the last name, you identify a very easy solution to remember, because Leontios Leontiades with addition of a Hadji in front. So you just remember me as Leontios. So what I will going to discuss today is about how we can use AI in order to create a scientific discovery. And we try to see how this discovery targets specific aspects of approaches. And you are a generation of an era that actually is born within AI. We are coming very old generation that has different aspects of approaching the problems. Now for you it's very convenient and let's say very natural. So I believe that going through this, and you are in the School of Physics, the discovery, the scientific discovery actually is embedded in the reason that you are here. So what is the era that we are living now characterized is mostly of the existence of many, many data. So the concept is that we have a lot of opportunities in order to see this data, but what actually we are lacking in a way is to ask the correct questions. So are we really asking the correct questions to the AI? Because usually what we try to do is to use AI in order to predict what we can observe. So we want to say classify an image, detect a disease, forecast an outcome. These are actually based in the context of an observable world. But imagine that there are a lot of information that is coming to what is not seen below, the hidden. And if you go to the scientific discoveries, you can understand that many of them are hidden. Can you see the gravity? Can you see the electromagnetism? Can you see the DNA by observing? So these things are in the context of what we are not observing and how we can try to understand what is the role of AI to move towards to this kind of scientific discoveries. So AI is not only the context to predict the visible, but actually to help to discover the invisible. This is the idea that I try to discuss with you today in order to understand the role of the AI, and specifically in the area of sciences. So if we use a lot of health-related information, as also Dimitri said before, you can see that we have a lot of data. So if we have a lot of data, this means that we have a better information, a better representation. The thing is that if we collect all this, doesn't mean that we have better understanding. So the idea behind is to understand the context. So how the AI can help us in order to see the information that is underlined and why. And this is, of course, what is, let's say, applied in the explanatory and explainable AI. But the idea is about understanding further what is underlined in a situation. So in order to do this, a lot of historical approaches teach us that we need to do a better representation. For example, you have different materials that are having complex patterns, and you want to classify them. If you do a representation in the color space, perhaps the problem becomes very simple. So you can see, and you know that we have the Fourier analysis that actually gave a lot of information in frequency domain, so understands what's going on in the frequency domain, and the MRI that give us what is inside the anatomy, the genomics give us the code. And now we have the AI, which actually does these Latin representations. So this is the benefit that we can see inside this context of using AI in a hidden space, in a latent space. So this latent space actually organizes what is seeable to other aspects where we can try to understand and translate these observations, but in another way. So the discovery actually starts when we have the observations, what we observe, to be representations. So it's very important to understand that this is something that the AI actually brings on the table, although, as I saw, there's a lot of structure in this perspective. And many times in your life when you have a problem, if you represent it in another way, you understand it better. So the representation, though, that comes from the AI, we see that comes from the latent space, as I said, but there all the things are mixed. So can we understand which is the mechanism that is underlying behind this representation in the observed data? So the idea is that everything is mixed in this latent space. You see the color code there and different representations in this space. But actually, can we understand and separate this? Because this compression actually does not necessarily mean that we can reveal the mechanisms that generate the data themselves. So what we try to see is how we can disentangle this. So the problem is how we can use a perspective that disentangle this information in the latent space, in the space where the AI actually works. And you can see the Benzio that says actually that the AI would understand the world if it could disentangle the explanatory factors of variation in the data it observes. So, meaning that it's very important, the perspective of disentanglement in this latent space, in order to really understand and explain the world. So the challenge here is that currently, when you have representations learning, like these variation autoencoders or beta variation autoencoders, actually they don't reinforce, they don't enforce disentanglement. This comes as an output. And it's an emergent property. It's not something that comes by the design. So meaning that these entanglement factors actually cannot give us interpretability, so we cannot interpret the results. So the idea is it possible to see this disentanglement, this separation of this latent space as a design idea, not as an outcome that came without control? So we work on these aspects by defining this context of forces of disentanglement. And the first is about Gaussian prior. This means that the latent space have very well-behaved and generalizable representations. Then we have the reconstruction. That means that we can disentangle this latent space, but this should also connect all together to give us the full latent space. And orthogonality. This means that this, between them, these parts are independent. So this reduces the redundancy. We don't want to have crossed mixed information from one latent representation to another. So this means that we have this disentanglement from the equilibrium of these three complementary constraints. So what we try to do is to create the context of disentanglement in the way that AI, let's say, operates. And the first idea was to see that when we have a signal, we can try to decompose the signal in different parts that it has inside. So this decomposition actually provides us information that are frequency limited, and we know exactly in which spectrum its part of the signal lies. So this gives us this information that actually we have a complex physiological signal, let's say an EEG, where it has different waves inside, and we want to separate in different frequencies of the factors and the parts that already have the oscillatory modes actually that compose the signal. So what was the idea is actually to have, for each part that is coming from the signal, to have a different encoder and create different latent spaces, like decomposing actually the latent space. So we can create different, as you see, Z1, Z2, Z3, Zk, that actually represent this disentanglement. So we start from the signal, we decompose it, and then we represent this decomposition in the lattice space, instead of having one signal represented in one lattice space. So in this case, we actually suggested this variational decomposition autoencoder, where you can see here the classical variational autoencoder that actually creates this latent space, as I saw before, coming from one prior distribution. And now we have different latent spaces that actually come from decomposed parts of the signal and create the new representation. And then if we apply here the three forces that we said before, actually we can create a new way of creating a representation that actually has pre-processing that gives us the decomposition and at the same time decomposes the latent space in separate small, let's say, latent space that represent actually the signal. I will not go through the details here, but you can see that there are different perspectives. The only thing is that you can see is that on the right-hand side, there is an inference model that actually uses the information from the other space, except of the one that is currently applying. So you see there xn, and then all the other latent spaces, except of the one that is participating. So what we try to do is, as an application, is to see how we can analyze this in the voice. And the voice is a lot of information that can be like in a small, let's say, a short time. We can have milliseconds, or we can have seconds. We can have vowels. We can have sentences. So you can try to understand how this signal is decomposed. You see the tau prime has the different parts of the signal inside. And then each part of the signal comes to a different separate latent space, and all of them create the separated disentangled common space where the AI can work. So we arrived by design to this context, not as an outcome. Okay, so we can have different scales. We implemented this in a different way of training. and we apply the problem of speaker identification and phonetic content. You can see here the different representations where you see how the variational decomposition autoencoder actually creates very nice, smoothly separated spaces inside the latent space. So this is what we wanted. We wanted the information to be disentangled in this latent space, go smoothly in a Gaussian distribution in 3D, and then we have the perspective of orthogonality and the perspective of integration all together create this space. So this gives us a lot of capabilities. You can see here that we have in real speech, we have the analysis that based on this method, we increase the disentanglement, we increase the robustness, and in this perspective, we try to show that by design, we can separate the space where the AI works. So the takeaway so far is that we have a different way of approaching the latent space, which is the representation of AI, by imposing a separation of the latent space of disentangled parts. And this gives us better understanding of the real world. But this gives us better understanding of the hidden physiology. So this is the context when we want to go to the real life and we go to the human being. So, for example, we have a different representation. We have the brain, we have the heart, we have the kidneys, all this, and we want to have a representation, disentangled representation in this space. So meaning that we want to show a biological meaning behind this disentanglement. So to identify from which instrument, for which organ, for example, has the pathology and how this, let's say, contributes to the general health of the patient. So we did this, and we tried to understand the pressure, the hypertension. So usually when you have hypertension, you just measure a number, and you are hypertensive. But perhaps we can have the same number exactly, but have a different source of the problem. So what we try to do is this disentanglement to have a representation in the organs. So we have all these different organs, so we have a multi-organ, multi-modal representation. In this way, we can stratify the people in different trajectories, and we can give them different scores, which actually this can relate with the cause of the problem. So we have the same exactly hypertensive number of the pressure, but for me it's the brain, for you is the kidney. Now the doctors, they don't do this. They just take the hypertension, the pressure, and see what is the level. So what we did is exactly this in order to reconstruct a latent physiologically explained space that actually quantifies all the invisible multi-organ damage. Again, an example of what we see with the pressure, but we don't see with the multi-organ organ damages. And the process was exactly like this. We have the data collection. We created a constructive representation in order to create representative groups of healthy and controls. And then we did some anchors by taking the severe cases and the healthy cases, and we did a PCA, contrasting PCA, in order to reduce the parameters. And as you can see, we create a contrastive trajectory where we can show where is the health situation and where is the disease. Actually, from my perspective, disease is another level of health, but it's a different trajectory. And based on this, we can have a score. We can characterize the severity of the specific organ. So we have this hyper trajectory and hyper score. And you can see here, we apply this in Biobank, which is a very big data set from UK, about 27,000 patients. And we see the different trajectories. You see the small icons that relates with the pathology, where it's in the kidney, on the lungs, on the heart. So it shows exactly which trajectory is related with. And also to validate this, we validate externally, and we saw that we have the same trajectory as identified before. See, this gives us actually the pathways of the disease projection. And if we go further and say how this hypertensive score affects the survival, let's say the time across to the event-free probability, we can see actually that we have different ways of reducing the time when you have the next event according to the severity, the hyperscore, and which trajectory you are. And you can see this on the right. You can see the blood pressure. So this is what is now statistically is used. So you go the blood pressure, they put you in a scale based on this number, and they show the times that you have the event time probability. And on the left-hand side, you can see the estimation that came from the hyperscore and hyper trajectories. So you can understand that we have better separation in terms of how these different categories are expressed. And this also can be done in terms of different organs of the hyper trajectory. And most importantly, we identify phenotypes. So as I said before, if you belong in the specific trajectory, for example, trajectory 1, the basic problem comes from the heart. But if you are in trajectory 4, the basic problem comes from the white matter of the brain. So this is very important to understand the source of the problem. And that's why we have this kind of discovery that comes from the data that are not observable, as we just said at the beginning. Another way that you can understand the context of the disease is that you have to consider this not as a state, actually, because it's a kind of dynamic perspective. So imagine that you have some symptoms and say, this year I feel worse than the previous year, but you just represent this severity in terms of symptoms. What happens if you represent this in the trajectory, as I showed before, in the latent space? So you have a manifold of the healthy representation and you have a manifold of the disease representation. So you move in this manifold and we are all, let's say, healthy and we are moving this manifold, but then something happens and we shift and go to the disease trajectory. But we have the same disease, but we have a different personalized perspective of trajectory in this manifold. So everything becomes of trajectory concept. So this is not a state, actually. So what disease does to this patient is not the important, but where is this patient along the disease line? So this is the idea. We create this context of disease trajectories, and this is what we are proposing now in a very recent article we are writing. It's about moving from the digital biomarkers, because the previous, let's say, decade, the context was used also by the matrix a lot of information in order to create representation of the health status in the digital space. And this gives us the digital biomarkers that actually are important in terms of very high density in sampling, because you have a smartwatch that this time measures my heartbeat and all the other things. So these are digital biomarkers, but we have to move on to what we call AI-enabled digital disease trajectories. So the idea is actually to understand of these transitions in the manifold, and it's not a kind of digital twin that I have a digital thing and I see how it goes, but it's the perspective of how we dynamically see all the time the representation in the latent space, in the way that AI actually acts. And we are implementing currently two big projects. One is called AI prognosis. It's actually in a Parkinson's disease, because there is a very big problem. You can have Parkinson's disease for 15 years, 20 years, and you don't know that you have Parkinson's disease. So there are a lot of shifts that are very subtle towards the disease manifestation that actually, if I ask you now what is the symptom that you know for Parkinson's, is tremor. But there are a lot of symptoms that are non-motor symptoms. Constipation is one of these, for example. Depression is one of these. So there are things that you don't see, but happening. So in this project, actually, we try to do these trajectories by identifying these biomarkers, but at the same time, creating a representation in progression in the risk, and also how the medication given to a patient, what are the side effects, what is the drug response. So there are all this information that actually can provide tools to the physicians, at the same time provide tools to the patient as well, and to the policymaker. And a similar problem is about the problem psoriatic arthritis. Perhaps you don't know what is psoriatic arthritis, but it's the next stage of psoriasis, which actually creates an arthritis for patients that already have psoriasis. And 30% of these patients of psoriasis move to psoriatic arthritis, and nobody knows why. So the idea is this hidden representations and non-observable situation to be exposed during this project. It's actually what we try to do in these perspectives in order to create the digital space representation based on the digital biomarkers and using this latent space to see how someone shifts from psoriasis manifold to psoriatic arthritis manifold. And of course, there are different tools for controlling this for the patients and the doctors. So the main idea is that you don't see the AI digital disease trajectories as only specific disease application, but actually it can be in a generalized perspective. So we can see it as a continuous precision care. You can go to multiple chronic diseases. So this is the second part that actually shows that this latent disentanglement is transferred to physiological explanation that provides the new way of seeing the trajectory of a disease in a latent space trajectory. Now, if we want to do this in the clinical practice, a lot of limitations currently. So you can see that we have evidence, we have longitudinal modeling, we have robustness in algorithms. The clinician has to accept it, which is not so easy task all the time, to be interoperable, reimbursement, and also the patients should accept. So this means that these are the move of the future of the digital medicine, actually. So it makes much better disease representation. So imagine yourself, you are a new generation that goes to this perspective, not just a disease characterization. So having all these sensitive aspects of the health and representations in the latent space, another question is about how the AI can collaborate with the humans. So what we have to show and to see is how we create this co-intelligence, which is very important to understand, to translate all these ideas in practice. So we can see that we have in the co-intelligence and distributed actually cognition. So we have the people and the tools and environment. Actually, you are using every day different tools for you to have some decisions that 5 years ago did not exist. Also, have to have an extended cognition, so the tools actually become part of the thinking. And also we have joint cognitive systems where we have the humans and the AI to think together. So in this way, we go to a co-intelligence between human and AI in the aspects of having this hidden representation, the hidden physiology, the hidden disease trajectories to lead to scientific discovery. So it's a kind of companion. And for Greeks, if we go back to our ancestors, we can base our knowledge actually to Aristotle, which has these three words, logos, ethos, pathos, which is very important to understand how we do this in the co-intelligence. So we're talking about the logos, which is the reason and the knowledge, and can be applied in a cognitive AI. We talk about the ethos, which is the values and the trust. We're talking about the ethical AI. We call it pathos and the human understanding and empathy, which is empathic AI. We are working now in the context of creating some perspectives of ideas that perhaps look very humanized, and we can see if they can be applied in the AI. For example, can AI feel pain? Is it possible for the AI to feel the pain? and what pain means to the AI, and how an empathic AI that feels the pain can behave to the humans in the collaboration and co-creation. So how we can see the perspective of pain, for example, acute pain, which is used for homeostasis. We can have chronic pain. We can have psychological pain. Can you imagine your AI to have all these capabilities? Is it possible to provide these human works in this perspective? Because a lot of information comes from the biological systems, which actually all the deep learning and the convolutional neural networks are based on the brain and the way that it works. So why we need pain? Why brain has the pain? Why it's important in the decision making? So can we do this perspective in the AI decision making? Can we do a latent representation of the pain? Can we have a cost function that actually can be implemented in a way to lead the decisions that someone takes? Because this is happening in our brain. When we have a pain, we take decisions. It's not the same if you don't have a pain. And even through the mirror neurons effect, we understand through the empathy of the others. So how can an AI understand the empathy, can feel your pain, although you don't actually are in pain? So these aspects, based on what I'm saying here, is about the way that we can collaborate in terms of taking the basic three words of logos, ethos, and pathos in practice. So the idea behind is to understand, as I saw before, what's happening in the non-visible world. We discussed today about, I've showed about the hidden representations, what the data are really telling us, the hidden physiology, what is happening inside the body, the hidden disease trajectories and how the disease evolves over time, the continuous precision care, how we intervene and improve outcomes, and the co-intelligence, how the science advances together. So the question is for you, take away how you perceive the role of AI in your life in terms of scientific discovery, how can help you in this perspective, and remember that actually the things that we have to understand is the scientific discovery begins when the observation ends. A lot of things you have to see to believe, but science also telling you that are there long before you see them. So thank you very much. I'm open for any questions.
You talked about AI's ability, ethical and empathic ability, but I'm interested, what do you think AI would be able to balance it, considering it is a purely logical system, and that AI is based on humans, and we are very, not very structured, like we tend to lean more emotionally. When something annoys us or impacts us, we don't really take the time to process it and we react with emotions. How do you think it will play out with AI? Will it be, again, logical, or would there be a risk for it to kind of lash out emotionally like humans?
So it's an angry AI, actually. Will be an angry AI, you mean? Yes. Structurally, our brain, as I said, I mentioned the word mirror neurons. Actually, there are specific neurons that exist in the brain of the humans. And these represent actually the real world inside us. And the empathy actually comes from there. If we take out these mirror neurons, then you will not feel the empathy. And this is totally started with a random experiment with monkeys where they had the context of seeing someone take peanuts, and we have a fire in the motor cortex. So this is the way that all the children and everybody learns from mimicking the others. So this is the context of seeing and doing. Okay, so the baby sees the mother, does brushing, takes and brushes in the same context. So this was the first discovery of mirror neurons, 2004. And then they saw that actually this is shifted to the empathy, to the emotions. When you see a football game, for example, while you are screaming, you hit yourself down, up and down, when you are not playing actually. It's like a part of the player is inside your brain. And you see this representation in yourself. So if you see the firing, you will see about 8 to 12 hertz, you will see these MU waves. If you get an autistic kid, these mirror neurons are not well developed. So that's why it will not see the social interaction. So it sees you, but it doesn't understand the context of empathy, according to the level of the spectrum, of course, but it is done in this perspective, that these mirror neurons are only for humans, and this creates the social aspects, the social need of the people. Okay, Aristotle said that if you are alone, are you a beast or either a god? So this is the context of having these mirror neurons in your brain and understand the pain of the other. When you see someone in pain, you feel that you are in pain. So taking into consideration this perspective and translating to the AI context, we can have this perspective of mirroring the emotions in terms of empathetic situation. And when we're talking about co-creation and collaboration and co-intelligence, it's like we are working together, but the AI perhaps can understand that you are in a situation that you are very stressed, and 70% of your decisions when you are stressed were wrong. So this information can come as a kind of a sliding responsibility between the AI and the humans in terms of co-intelligence, and having the empathetic aspect inside, we can understand that the decision is affected, otherwise will not be affected. So this interaction is very important. But at the same time, Europe is focusing in new ways of representation of AI because they want to go outside of LLMs. They go outside of situations that actually are quite difficult, let's say, to converge in high scales. And they want to go to biology-inspired solutions. You know that your brain works and makes all these complex decisions and analysis. You know how many power it uses?
No, I don't know personally how much power.
20 watts. 20 watts. Okay, so imagine how the biological design is so optimized that that's why Europe is funding now and has calls in order to go to deep reasoning, abstraction, and planning outside of LLMs, outside of this context of data-driven, but take into consideration what the brain actually has, all these areas, and how we can understand this. We created the composition of a signal based on the cochlear, so we name it cochlear decomposition, actually decomposing the signal in the way that cochlear decomposes the frequency in order to understand the sound. So ideas that comes from the brain and this empathic AI and the pain inside the way that the AI is developed can go to these structural characteristics of Latin representation. So you don't represent only, let's say, the frequency characteristics of the signal, but as I said, you can represent the perspective of the pain. So can we have a factor that actually weights the other factors in terms of pain representation in this latent space? So this is the idea of trying to see. There are other aspects, for example, does the brain, the AI, sleeps? Because your brain during sleep makes a lot of work. That's why it's important to sleep. So can you transfer this ability in the AI? Does the AI ages? Can we have an old AI and a young AI? What is the difference? You have an old professor and a young professor. You consider that you have AI like a very robust young person that does everything. But what is the decision efficiency when you have a matured, let's say, professor and a just started professor? Capabilities are different. Can we transfer this perspective like aging AI? So these concepts are the new ways, let's say, to understand how the AI perspective can come based on these three words that Aristotle just mentioned, said so many years ago.
Thank you. Thank you very much.
I believe AI is hungry, and I'm keeping him from lunch, so.
Okay, I am a volunteer, but can I also ask a question? Is that okay for you? Okay, so you mentioned the decomposition of the signals, and I also heard that you're actually quite educated in music. Are there any applications of this signal decomposition in the field of music?
Yes. The field of music is totally different perspective because there is what you can see music is like when you hear something, a composer has composed the piece. As you hear it, you get the derivative, which is part, and what you are doing, you finally get the integral. And the amazing thing with music is that each integral has a different result for each one. So if you want to see where the decomposition can go, perhaps you can go to the beginning in the mind of the composer, because he actually tries to organize the situation. So there, the composition can be in different perspectives, not only in the frequency domain, but you can do it in many ideas. For example, you can do in the spatial perspective, how the sound is moving around. If you have an orchestra, the way that you orchestrate, you have a different spatial effect. So how you decompose this? You can do it in the spectral decomposition, so you can do a kind of specular sculpture. So you can have different parts of a sculpture in the spectrum, and you can compose and decompose this. You can do a decomposition in meanings. So why you want to have a complex meaning to decompose in different ways. So you can use other perspectives. For example, in my work, I use fractal analysis and game theory in order to decompose the behavior of two parts of an orchestra. So they're just playing a game, but actually they're producing music. So the decomposition idea is always in a way to handle the information in different details instead of having a total perspective. And these details can give you some output. Again, this latent representation comes to the brain of the composer, which actually has the capability to freeze the time, because I can work in 3 real-time seconds, 1 week. Okay, when you listen, you hear the music, it's 3 seconds. But for me to write it, perhaps I spend 1 week time. So these parts are important in terms of going to the composer idea. Then you can see other aspects in terms of interpretation, which try to express what is the idea of the composer. That's why there are differences in the quality of the concerts. And then you can see, let's say, where we have the perspective of understanding the music from the audience. One or two of my pieces, three of my pieces using EEG device. So I'm using an EEG device to capture the data real time from the performer and the conductor. And actually this drives the music real time. So there are a lot of things, that's why I'm naming it biomusic. We can use the body as an instrument and all these aspects of real-time thinking and feeling from the musicians, and perhaps we can extend it also to the audience. Thank you very much.